All right, I'm just going to do a quick introduction to water potentials so that we can discuss some of the mechanisms of phloem transport. So, first of all, just a description of what water potential measures. Um, so, water potential is a way to quantify the potential energy of water. And so, if you think back to your chemistry classes in high school, probably you remember that all of the molecules in the air and in liquid, they're moving just a little bit, right? There's a little bit of shaking going on, and that's like a form of potential energy. Um, and there's other ways to change the potential energy of water, but that's like one way to think about it, is that those molecules are moving around, and anything we do to increase or decrease that movement in that energy reduces or increases its water potential and its potential to do work, right? That's what potential energy represents. So, a way to quantify potential energy of water, the reference that we use or the value that we've defined as 0 is pure water at standard temperature and pressure. And that's 20 degrees Celsius is standard temperature, and basically sea level, which is 101.3 kilopascals, is standard pressure. So that's what we define as 0. So anything that would decrease the potential energy of water would make the values more negative. And then anything that would increase that potential energy would result in a positive value. So things that would decrease the potential energy of water is if we add some solutes into that water. So remember, our reference is pure water. If we add molecules, we add some solutes like salt or sugar into that water, those molecules are going to interact with the water molecules and reduce the movement of those molecules, thus reducing the potential energy of that water. Also, if we were to put like some tension on that water or a vacuum, remember, water molecules are adhering to each other. And so yeah, sorry. I was thinking about whether it would adhering or cohering. But anyway, we'll talk about that later. So if you were to like basically pull on a chain of water on each end, almost like if you had a string and you're pulling on each end, you can do that with water to some degree, and that would reduce its potential energy, because when it's under tension, those molecules cannot move as rapidly or as much. So then on the flip side, anything that would increase potential energy creates that positive value. So if we were to pressurize a system or heat up the system, those molecules are going to be moving a lot faster. The other thing you could do is you could move the water up above sea level. And so that I think the better way to think about it is like if you, all right, my cup of coffee has some potential energy, and the further I raise it away from the desk or the floor, the more potential energy it has, because that's the potential to do work. If I drop it, it's going to be moving back to Earth's surface. So, and that took energy. Okay, so the one of the main reasons I point that out is because in plants, pretty much there's things that reduce potential energy of water, and there's things in the plant that increase it, but the net effect is to decrease it. So pretty much when we're talking about a whole plant or plant tissues, we're talking about negative water potentials. Okay, so water potential gradients in trees are under static conditions, so where they're not changing really rapidly. They change over time fairly slowly, but we consider those, like the time frame that things change, we still consider these static conditions. And when the water's not moving in the plant, then that's a hydrostatic condition. And even when the water isn't moving, we have gradients of water potential. That wasn't what I wanted to get into. I forgot that was the title of the slide, so I wanted to explain it. What I really want to talk about is the components that go into defining or kind of creating the potential energy of water in a plant. And there's really 4 main components. 3 of them will be really important. 1 of them we tend to ignore. But we use the symbol psi to represent water potential. And so psi sub W is the water potential of some plant tissue. The psi sub S is the solute potential. And remember, if we add solutes, it's going to interact with the water molecules and decrease potential energy of water. So solute potential has a negative effect on water potential. It's going to push it to lower potential energies and more negative numbers. Pressure potential, on the other hand, is going to increase potential energy. So that would be like if we were pressurizing a system, we would be increasing the potential energy. Inside plants, what we're talking about is the cell. So the cells, are surrounded by a cell wall. And if the water fills up that cell wall too much, the cell walls are pushing back onto the contents of the cell, and that's where the positive pressure comes from, is the pressure of the cell wall back on the contents of the cell. Matrix potential is a negative impact, and that's when water molecules are held to the surface of particles. So the place we really think about matrix potential is in soils. So if you've got two soil particles side by side and there's a little droplet of water adhered to the surfaces of those two particles of soil, that's matrix potential. It's holding that water molecule in. And so those are negative numbers. And then the last one is gravitational potential. So the further the tissue is of the plant, the further that is away from the surface, the more positive the gravitational potential. And this is a fairly small effect on short plants. So in grasses, for example, or shrubs, we just ignore it. But in really tall trees, it can actually have a big impact on water potentials.